invitation to speak here today. I'm really excited to be talking about what ended up, sometimes with a lot of research projects go, this sort of multi-year rabbit hole into thinking about ensemble methods, and particularly ensembles of neural networks, and effectively, what we can say about them as far as uncertainty quantification goes, and maybe how a lot of the intuitions that we carry from us, from say like, introductory machine learning classes about ensembles may not necessarily apply when we're thinking about ensembles of large neural networks, especially in the context of uncertainty quantification. And so, a lot of what I focus on in my research is sort of the central question of how do we make reliable decisions with machine learning models, especially when, the notions of uncertainty that we might be getting out of these models are heuristic or approximate at best. And why this then sort of led me down this rabbit hole about ensembles is because if you look in the literature, there's so many examples of uh, essentially researchers using ensembles whenever there is this need for uncertainty coming from predictions of neural networks. So there was this, seminal paper, this deep ensembles paper, which was the first to really demonstrate the power that training multiple neural networks and using them all to make predictions uh, would give you a good notion of uncertainty. And since then, there's been all sorts of papers that have come up, saying we should be using ensembles, especially when we care about potentially identifying out of distribution data or having well-calibrated uncertainty estimates on out of distribution data. Many people using ensembles in applications where we want uncertainty as part of the decision-making pipeline, such as in reinforcement learning or in Bayesian optimization. And the intuition for why ensembles, would make sense, especially for these applications that need to be uncertainty aware. There's this really nice, compelling story that we can tell ourselves. So let's imagine that we train a bunch of neural networks. Um, just the standard recipe for deep ensembles here, which I want you to keep in your mind. Of course, there's slight variance, but the general recipe is that we're going to have multiple copies of the same architecture, although there can be some slight architectural variance. We'll talk about that later in the talk. They're generally going to be trained on the same data set, so no techniques like bagging or anything like that. They're all going to be trained independently, so no boosting. The only differences are going to be the parameter initialization and the mini batch ordering when we're training. But that randomness that we get, because obviously training a neural network is inherently this non-convex optimization problem. This randomness that we get from the different initialization and training the data ordering, that's going to be enough to make sure that all of these neural networks are going to have learned different functions. And so if we pass data that looks similar to what we saw during training, so so-called in distribution data, then it's very likely that these independent copies of the neural network are all going to make roughly the same prediction. Of course, now if we feed in so-called out of distribution data, which isn't necessarily super well defined, other than that it's data that we expect to look very different than what we encounter during training. Well, if now a neural network sees this out of distribution data, there is nothing inherently constraining the networks to make any type of prediction. And this inherent randomness that we have, through the initialization, through the SGG training, should, in theory, cause all of these networks to make different predictions. And so if we look at then the variance of the predictions that are coming out of an ensemble, this should give us a pretty reasonable signal for how uncertain we should be about the predictions that are being made. If all of the ensemble members are making the same prediction, we should have high certainty. They're all making different predictions, we should have low certainty, high uncertainty. And in general, this recipe is very good at getting well-calibrated uncertainty estimates. So what I'm showing here is from the original Deep Ensembles paper. This is what is a reliability diagram. And this is basically assessing, if we're just sort of like measuring, the frequentist consistency of our uncertainty estimates. So effectively, if we have 50% confidence on a bunch of samples, right, we should actually be correct 50% of the time. So here we're plotting, four samples with a given confidence level, how accurate are we? We want to try to hit that perfect identity diagonal because that would mean then that the confidence estimates that we have reflect the ground truth probability of actually being correct, from this very kind of frequentist notion of uncertainty. And we can see that this ensembling recipe and the uncertainty estimates that we get, again, which is using that variance amongst the ensemble predictions, is actually getting us pretty well calibrated uncertainty estimates. So that's a really good thing. But one big takeaway that I had as part of this project and something that I'm really carrying forward in a lot of my research is calibration isn't everything. Calibration is just one component that we like out of an uncertainty estimate. Calibration basically tells us that when we have an uncertainty estimate, it is in the language of probability. But right, there are many different uncertainty estimates that we could have that satisfy calibration. What makes for a good uncertainty estimate is one that's going to allow us to make reliable downstream decisions. So one kind of, of course, that can take many different flavors. One that's often seen in papers that's really easy to test is so-called out of distribution detection, where our goal is to use the uncertainty that we would get out of a model, or in this case, the uncertainty we get out of an ensemble, to try to identify predictions that might be out of distribution, predictions that might be, or sorry, data that might be completely unlike anything we saw during training, and therefore we expect like nonsensical predictions out of our model. So this is a decision in that we are trying to determine is this particular input out of distribution or not, again, using the uncertainty that we have access to. And so now if we start to like really dig into these uncertainty estimates that we're getting out of ensembles, we see some peculiar things happen. What I'm plotting here is just a histogram of the amount of uncertainty. So like the variance that we get out of the ensemble for predictions that are in distribution, which is the blue line, and predictions that are out of distribution, which is the orange line. And what we can see from this histogram is, for most data points, we're getting generally fairly low variance. But when we are looking at the out of distribution inputs, the orange line, we're seeing that that line is a little bit higher for some of these higher levels of variance, which means that for out of distribution data, we are more likely to see, or we are more likely to get predictions that have high variance. And that's a good thing. This is kind of going with our intuitions that with this out of distribution data, things that don't look like what we saw during training, we're more likely to express uncertainty. But then when we dug into this a little bit further, when we conditioned those histograms now on the outputs that any individual model was making, we saw that this difference started to go away. And effectively, this is kind of a complicated result, and I don't want to, dive into it too much. I'm happy to chat about it more during the questions. But effectively, what this tells us is that even though we were seeing this higher variance on these out of distribution data points coming from ensembles, really where all of that signal was coming from was just the types of predictions that were being made by any individual model in isolation. So what we are this ensemble variance isn't necessarily providing us an additional signal that we wouldn't have had access to from a single model. And this was a little troubling and strange to us as we were thinking about it, because there's this whole idea that there's this variance that we're getting out of the ensemble, being able to see what are the predictions that multiple neural networks are making. This should be providing us some additional uncertainty that should be guiding our decision-making processes. There's additional information that we wouldn't have had access to if we had just used a single model in isolation. And effectively, what this result is telling us is that all we're seeing from this ensemble variance is basically just replicated information that we would have otherwise had access to from just a single model. We again, that's a fairly technical result from one of our papers. We weren't the only ones to sort of observe that when we are trying to use uncertainty in these downstream decision-making tasks, ensembles don't necessarily provide all of the promise or that this intuition tells us that they should. Here is a plot from a paper that was looking at using ensembles for Bayesian optimization. If you've never seen one of these plots before, basically the way to read it is you want to try to end up like as high in the upper left corner as much as possible. This is basically showing you you're trying to optimize a black box objective function. In this case, optimization equaling maximization. So you want to try to get high objective function values, and you want to try to get those high objective function values as early as you can in the optimization process with as few function evaluations as possible. The black line here on these plots represents what we get out of ensembles of neural networks as opposed to some other approaches, many of which involve other Bayesian approximations to neural networks. And what we can see is that this black line generally ends up performing not too great. It generally ends up being somewhere in the middle of the pack or kind of at the bottom of the pack, where it's the slowest to make its way up to these high function evaluations. So again, ensembles are not providing good uncertainty that would allow us to do this good decision making, this good sequential decision making, this good Bayesian optimization. And the hypothesis that my colleagues and I had is why these uncertainty estimates that we're getting out of ensembles maybe aren't leading or aren't living up to the hype that they have from this intuition has to do with the fact that we are ensembling over parameterized models. And this is a fundamentally different regime that goes against all of the intuitions that we've developed about ensemble methods, sort of from our machine learning 101 classes and all of our classic analyses. So when I learned about ensembling in my machine learning class, I learned about it in the context of this bias variance trade-off, where um, here's sort of the classic bias variance trade-off curve, where we're seeing risk on the y-axis decomposed into its bias and variance components, and regardless of where we are on this bias variance trade-off curve, there is an ensembling method that will help us reduce risk. In the case of if we have a bunch of really high bias models, so think weak learners, we know that boosting is this tried and true ensemble method that is guaranteed to reduce risk. If we are then fall on the other end of the spectrum on this high variance but low bias, so imagine we have some like very large decision trees, then we know that methods like bagging or random forests, these will be ways to counteract the variance that any one individual model has. And so again, tried and true method for producing an ensemble that is better than any single one of its parts. We now know in the last, say, 7 years or so that this bias variance trade-off graph is actually incomplete. And that if we push past what is called the overparameterization regime, which is basically the point at which we have individual models that are capable of memorizing the data that they are trained on, once we end up now with overparameterized models that are in this case like underspecified, we actually continue to see a decrease in risk. In this case, we see that variance continues to go down as we make our models more and more powerful. And this is arguably where neural networks lie on this side of the curve. However, now it's not really clear what ensemble method should work in this regime, or even if ensembling methods are reasonable or should work in this regime, because a lot of the intuitions that we carry about ensembles really rely on these classical methods that apply to this one half of the bias variance curve and not this new half. And so this hypothesis of there's something fundamentally different about ensembling over parameterized models led to several investigations that both one confirmed this hypothesis theoretically, but then two thought of what can we do now with this knowledge? Where do our current intuitions break down and lead to pathological behavior, and where would some totally wild ensembling methods actually work pretty well in practice? So very briefly, in the next couple of slides, I want to describe sort of a analysis that we did, a theoretical analysis that demonstrated how overparameterization impacts ensembles, and specifically the uncertainty estimates that we would get out of ensembles. So to try to analyze this from a theoretical perspective, and I guess before I start there, a lot of this theoretical analysis was motivated first by empirical findings that we had with neural networks. And what we'll see is that even though what we're going to be looking at is going to be a simpler class of models than big neural networks, we'll see that a lot of the findings we have here actually carry over and hold empirically for neural networks as well. The model that we are going to analyze is what is often referred to as a random feature regressor. So what we could think about this as is this could be a neural network where we randomly initialize and then fix most of the weights of this neural network. And the only thing that we're going to train is the last layer of this neural network. And so this is the common approximation that's made in the in deep learning theory literature. It's an approximation that tends to hold pretty exactly as things get really large, due to sort of like neural tangent kernel effects. And what's really nice about this approximation is that we get essentially what is a linear model at the end of the day. This representation that we're getting out of all of these fixed hidden layers, which I'm calling phi of x here, right? Like that's just going to be some sort of fixed basis expansion, fixed feature representation of the data that I'm passing into it. Now all I'm training is going to be this, final set of weights, what I'm calling theta here. And so our model is phi of x transpose theta. That's going to be the predictions we get out of this neural network approximation. And of course, the only learnable parameters I have here is with theta. So this is basically a linear model on some fixed feature representation. And it's a fixed but random feature representation. And that randomness is going to be really crucial as we want to try to analyze this. So what my colleagues and I set out to try to compare was, let's imagine now that we have a fixed feature budget, right? So we can imagine that we have phi of x here. There is going to be a total of m times d features in this phi of x. Or rather, alternatively, if you want to think about it, we have a budget for m times d learnable parameters that we want to have in that final layer. And now there's a couple of ways we could think about divvying up that feature budget. We could either create one very large model that's using all MD features. And so this is now going to be this linear model with M times D features, M times D learnable parameters. Or we could divide those features and those learnable parameters into an ensemble. So we could have M ensemble members, each of which is acting on a subset of D features. And again, these are all randomly, all of these features that we're getting to, or that we are using, these are random features that are sort of fixed at initialization. So if I'm subdividing these features into different ensemble members, each of these ensemble members is going to be different because they're all going to have access to a different set of random features. This is sort of the key here is that I can either choose to, again, use all that feature budget in one model, or I can divide that feature budget across many models. I'm going to assume now, though, also that D here, which would be the number of features that each ensemble member gets, is going to be greater than N. So we're always going to be considering overparameterized models here. The difference is it an ensemble of like kind of big models, or is it one very single, very, very large model? And when we're thinking about ensembling, all we're thinking about doing is just a simple arithmetic average of the predictions made by the networks. So this is probably the most technical line that I have here. But when I'm thinking about this random feature expansion that I'm using, so again, these are going to be the random features that were, come from initializing this neural network approximation that we're fixing here. I can think about what is the expected inner product between any two sets of features that I have. And right, the actual inner product of those features is, of course, going to be random due to the randomness that I have in the way I'm constructing my features. The expectation of this inner product is going to be, some sort of positive definite kernel, which I could also think of as if I were to take my very large model and think about what happens as MD goes to infinity. So basically, as this model becomes infinitely wide with again randomly initialized features, basically if this model becomes infinitely wide, you could think about I'm going to have all the possible features I could have from this distribution. This model is going to then converge to something that it's pretty easy to derive this. It's going to converge to what is known as the ridgeless kernel regressor. So this would be a kernel machine, or kernel ridge regression trained using the kernel that is the expected value of the inner product of these random features. It's ridgeless because we could think about what is going to happen as our ridge parameter would go to zero. This is again, a fairly established result. It's not too hard to derive, right? This infinitely wide random feature model is going to become something nice and deterministic that we can, easily analyze. This is just like, basic kernel machines. The surprising results that we came up with was we were thinking now, well, what would happen in this other case? Let's imagine that we have instead of having this one model that's becoming infinitely wide, what if we now have a bunch of finite width models? Again, they're going to be finite width, but we're still imagining that each of them are going to be overparameterized. But we're now thinking about what happens as we bring the number of ensemble members to infinity. So it's a single infinitely wide model versus a infinite ensemble of finite width models. And we expected that there was going to be some sort of difference between, what the ensemble, this infinite ensemble versus this infinitely wide model converge to. And crucially, there's plenty of papers that show in the underparameterized case, there is in fact a big difference. But what we found is in the overparameterized case, so where each of these finite width models still has more parameters than training data, it also converges to the ridgeless kernel regressor. And we managed to prove this with like very, very minimal assumptions. Of course, we're still making this assumption that, everything here is, fixed at random initialization, at least all the features. So, there's that assumption where it's, not the same quite as a neural network, but we were able to prove this with making very few assumptions on what the distribution of random features looks like. So just to sort of confirm that this in fact works in practice, what I'm showing over here on the left now is basically the set of just a simple one-dimensional, data set represented by these dots. The blue lines represent a bunch of these over-parameterized random feature regressors that we've trained. So we could think about each of those blue lines as representing a single ensemble member. And of course, each of these ensemble members are making slightly different predictions. We're getting, more variance from the different predictions, when we're further away from the training data. But now what I'm showing over on the right is what we get when we average all of those blue lines together. And the ensemble prediction, which again is going to be the average of all of these members, perfectly coincides with what is the kernel model, which again is the single model that becomes infinitely wide. So again, proof that our infinite ensemble is the same as the infinitely wide model. And just to also confirm, this is in fact a consequence of overparameterization. So what I'm showing here on this graph is, so we ran this experiment on a small data set with, I think it was about 12 data points. And on the x-axis, I'm showing the number of features that each ensemble member had. So so we're experimenting with ensembles with different numbers of features, and that dotted line again is going to represent the what we call the overparameterization threshold. So at what point we have now ensemble members with more features than training data points. And you get this kind of surprising hockey stick shaped graph where, right, when we are under parameterized, where each of our ensemble members doesn't have, as many features as training data points, there is a huge difference between what this ensemble prediction is making and what a infinitely wide model will be making. Again, once we cross it over parameterization threshold, that difference goes away. It doesn't matter anymore how many features each individual model has, it just goes away. And I guess finally, it's worth mentioning that we did replicate this experiment, actually in an earlier paper, which sort of motivated this theoretical analysis to show that this does seem to also generally hold in the case of, normal neural networks, no, random feature fixing on initialization stuff. So this plot's a little harder to read, but what I'm showing is it's basically a per data point scatter plot from models that were trained on the CFAR10 data set. On the x-axis, this is going to be, you can think about it as the predictions that are being made by an ensemble of, I believe it was some ResNet 18s. On the y-axis is the predictions that made by a single wide ResNet, so basically 4 times as many parameters. And there is a pretty high, R-squared correlation amongst the predictions that are being made by either the single very large model or the ensemble of smaller models. And very interestingly, there was this tight correlation regardless of whether we were making predictions on in distribution or out of distribution data. So ensembles of medium-sized models, still over-parameterized, are functionally very similar to single very large models. If you've kept up with me so far on this, now here's the punchline, what this result shows for uncertainty quantification, which I think I have been sort of like trying to digest and really understand the implications of it, and still trying to still processing everything that and trying to put it all together. So again, when we're thinking about using ensembles for uncertainty quantification, what we're doing is we're looking at the variance that we're getting out of the ensemble predictions. So let's just go back to Stats 101. Variance is going to be the expected difference between any single ensemble member and the ensemble prediction itself, right? The ensemble prediction is going to be, right, this arithmetic average of all the predictions made by each of our ensemble members. So ensemble prediction, difference between single model and the ensemble prediction. But now what we have from our result is this equivalence between the ensemble prediction and the prediction made by a single very large model, right? So again, we basically showed that, well, in the infinite limit, the ensemble becomes the same as infinitely wide model. We also have finite width guarantees as well in our paper. But putting these two pieces together, what we have is that um, if we have that variance is basically measuring the difference between a single model and the expected ensemble prediction, and an ensemble prediction is the same as the prediction we're getting from a single large model. What we have is that I could think about variance. The variance that I'm getting from an ensemble is the difference between any single ensemble member and a very, very large network. So, in other words, the ensemble variance can be thought of as the expected change in prediction that I would get from increasing the capacity of a model. And that was so. I'm just going to pause there, or not pause, but I'll say it again just to kind of like let it marinate a little bit. Um, when we're getting ensemble variance, we could effectively think of what that signal is telling us is how would my predictions change if instead of using, my resonant 18, instead I were to use a wide resonant 18. So instead, if I were to use a bigger model. Now, that might be very useful information. I'm not saying that that's totally garbage. It's an interesting notion of uncertainty. It doesn't conform with any sort of our standard notions of uncertainty, but that's kind of the big takeaway that we had from this result is that we don't really know what to do with this object, but we can't necessarily assume that it's going to behave like measures of uncertainty that we've come to know and love. Right. Typically, what I want from a notion of uncertainty, especially like if I'm thinking about like a Bayesian notion of uncertainty, which often people are trying to equate ensembles to, is thinking about how would my predictions change if I had more training data? And instead, what I'm getting is how would my predictions change if I had more model parameters? Not the same thing. And what we can see from various experiments and practice is that it's actually really easy to construct cases where those two things actually don't coincide whatsoever. So what I'm showing here on this plot is results from a toy experiment, which is plotting on the left-hand side this ensemble variance. So expected effects of increasing model capacity. On the right is showing what we would get from sort of like a standard Bayesian notion of uncertainty, which again should hopefully be telling us how would our prediction change if we had more data. And we can see like there's some similar shapes, but they are actually, quite different in practice, and that could have big implications on downstream decision making. So from this first part of the talk, I think that the key takeaways is that we could think about once we are in this overparameterization regime, ensembles are basically the same thing as really large models. And because of that, the uncertainty estimate that we're getting from ensembles is basically just telling us how would my prediction change if I had larger models rather than how would my prediction change if I had larger data sets. And again, to emphasize, this is specific to the overparameterized regime. If we repeated these analysis in the underparameterized regime, we would see something very different. We would actually start to see that, and there's plenty of literature to demonstrate this, that the uncertainty estimates that we would get from ensembles in this underparameterized regime actually do behave a lot more like uncertainty estimates that we would expect from like a standard Bayesian or frequentist analysis. Um, I guess,
Yeah,
oh,
may I
yes,
pause for some questions?
yeah, absolutely.
Yes, thank you for sharing the very interesting result. So I just wondering the variance you defined.
Yeah,
Let's say the model is already large enough.
yeah.
If we incrementally increase the size of the model, is it we are going to expect, the variance is going to become smaller and smaller and smaller, end of the day approaching zero. So that means
Yes.
end of the day, we don't have any uncertainty.
Yes. Yeah,
Right.
that's a really good point, and I'm actually gonna touch on that a little bit in this next couple of slides. But yeah, this is, I think, something that is sort of this like surprising counterintuitive phenomenon in this like double descent over parameterized regime where, right, like increasing capacity of models is actually variance reduction, where we're conforming more to some very strong inductive bias. So yeah, it's and this is kind of, if we sort of think about it with like kind of our classical brains, like right, or like especially with like a classical Bayesian brain, like there is like that's basically doing the opposite of what I would expect. Like typically, I think if I have a larger model that is more ill-determined given the data I have, I should expect my uncertainty to increase, as I add more parameters. And so I think this sort of like double descent phenomenon that really is due to this like really strong inductive bias that we're getting from optimization, like that's, I think, playing a huge role here in the results that we're seeing.
Yeah. I have a related question. It's about, do you see any connection with robustness?
Okay, yeah, that's a really interesting question. Yeah, with robustness. So, well, I guess like what we ended up doing some kind of basic experiments here, where again, if we're thinking about the ensemble prediction being effectively the same as the prediction we would get from a large model, then what we basically found is that ensembles don't induce any additional effective robustness. So there's been a couple of and I know that there's been some follow-up work that has sort of poked holes in some of this, but there was this line of work that was looking at what was called like accuracy on the line, that where typically what you would do is you would say like here's an in distribution test set, here's an out of distribution test set. You would evaluate a model's performance, um, both on the in distribution and out of distribution test set, and you could sort of plot it. And typically, what people found is there's a very strong correlation between a model's in distribution performance and out of distribution performance. So basically, you get a better model will generally perform better, or will generally be a more robust model. And we sort of found the same was true with ensembles, especially since ensembles seem to be sort of equivalent to these larger overparameterized models. So there's plenty of literature that says like an ensemble of say resonant 18s is going to be more robust than a single resonant 18. But if you now sort of condition on the amount of computation you're doing, an ensemble of resonant 18s is not going to be any more robust than a single wide resonant 18.
Okay. Okay. Thank you. Any other questions? Okay. Yeah, we have more. Thanks.
Great. Yeah. So kind of building off of this, like in this second part, uh, what I want to mention is just kind of some implications of this finding and backwards intuition. So I think what's interesting about this is there's definitely now, if we kind of approach, if we take this result and now we think about, okay, how do we construct better ensembles? I guess largely what I found is that if we follow our classical ensemble intuitions, we're going in the opposite direction. We actually might be making worse ensembles. And if we try some like totally harebrained ideas, we might actually end up building better ensembles. Um, so in the classic ensemble literature, right, there's, I mean, I think this also kind of holds true in this setting, right, is that how do we make better ensembles? We want to make sure that we have, diversity in the types of predictions that our component models are making, right? And if you think about, go back to this sort of standard deep ensemble recipe that I talked about, right? There's not necessarily a lot that is super different amongst these models, right? Again, they're being trained with the same architecture on the same data. Um, we're not doing any sort of like subsampling or like boosting or anything like that. All we're just relying on it is just sort of the randomness of SGD to make different predictions. And this feels like there is so much meat on the bone that we could, that is there for making better ensembles. If we were to say use somehow use models that weren't quite so similar to one another. So what would happen if we were to now ensemble models that had different architectures, or were trained in slightly different ways? Would that now introduce some additional variance amongst these models that might lead to better predictions, but also more reliable uncertainty quantification? And the answer is sort of yes, but not, there's not a ton of room to sort of make big improvements here. So What I'm showing here is a plot that we generated to help us try to analyze ensembles. And the idea is we can think if we think about sort of the error, and I'm going to just kind of do everything with mean squared error here. I know it's not really what we use in practice if we're doing a lot of like classification or other tasks, but the analysis becomes easy with mean squared error, and it basically, it's the same thing for any other type of loss. Um, if I think about the ensemble prediction that I'm making, where again, the ensemble prediction is just going to be, the expectation of the prediction that's being made by my individual models, the arithmetic average of that, just sort of doing again, like a simple kind of like introductory statistics decomposition, I can decompose what would be the mean squared error of my ensemble prediction into two terms, which would be basically the expected mean squared error from any one of my individual component models, so the component model risk, and then this variance term, which would be capturing like the how different my predictions are. Um, and so my ensemble, the mean squared error of my ensemble is going to be equal to the average mean squared error of any of my component models minus the variance amongst them. This now gives us a nice way to create these sort of level set diagrams of ensemble risk. So what I'm plotting over here is going to be, I can plot an ensemble on this plot over here, the scatter plot, where on the um, x-axis I'm plotting the predicted diversity. So, the variance amongst these ensemble members, averaged over the test set of data. And on the y-axis, I'm plotting what would be the average error that any of these models is making. And so that now gives me these diagonal level sets that correspond to ensemble performance. Again, I have sort of like two ways that I could think about making good ensembles. I could either have, models that are very diverse that are making very different errors, or I could have a lot of models that are just really, really strong, like really, really good component models. So, in theory, if I were to introduce additional sources of diversity into these models, so like again, thinking about what if I use different architectures or different training procedures, right? In theory, this should allow me to move across this x-axis over here, basically increasing the amount of variance, the predictive diversity, which would move me down these level sets, which would, in theory, produce a better ensemble and this does in fact happen in practice. So if we go from say a homogeneous ensemble to say a heterogeneous ensemble, where the idea would be instead of just making an ensemble of here's a bunch of ResNet 18s, what if instead I have here is a ResNet 18 compared with efficient net compared with VIT small, a bunch of models that all effectively get the same performance, but like have slightly different architectures. I will see this like slight increase in predictive diversity, which overall leads to a better ensemble. However, that pales in comparison to the performance gains that I would expect from what if instead of just having this slightly more or what if instead of like searching for these sort of free sources of predictive diversity, if instead I just used better models. That is ultimately going to be the recipe or that will produce the best ensembles. But what I will find is to move down these level sets, that's going to come at the cost of this predicted diversity. What we did is we took a bunch of models that were publicly available through various model zoos, and some models that we trained on our own, on CFAR and ImageNet, and formed various ensembles, both homogeneous ensembles and these heterogeneous ensembles. Homogeneous meaning same architecture, same training procedure. Heterogeneous meaning we ensembled models with very similar performance but slightly different architectures and training procedures. And the dashed diagonal line corresponds to the best performing ensemble that we had or that we found. And what we can see is basically there is this sort of like downwards, leftwards trend. If we want to move down these level sets, if we want to get to the best ensemble, really the best recipe that we have is just build better models. Those better models are going to be inherently less diverse. Again, like the question that we had earlier, essentially because, we're like as we move down this double descent curve, we're basically having models that are all kind of converging to the same inductive bias. And so this means like if we are trying to, if ultimately we want really good performance, we basically have a lot more homogeneity in the types of predictions that we're going to be making. We're not going to get good uncertainty estimates out of our ensembles because to make them better, we end up having models that perform a lot more similar to one another. Um, and just in the interest of time, I'm gonna skip that slide. Um, but so that's sort of an example where if we think about sort of like what would be sort of a classic technique that we could try to throw at the problem, where it really falls flat on its face, and where again it might be leading us in the opposite direction of what would ultimately lead to better ensembles. Um, I guess the good news is not all hope is lost, but it kind of requires some, out of the box thinking and trying some ideas that, honestly, if someone had proposed this to me 5 years ago, I probably would have, laughed and said, there's no way that this would possibly work. One thing that a really fun project that we had last year was thinking about could we create just like simple ensembles? And here, when I'm thinking about an ensemble, I'm just thinking about combining two models, and where it's now two models with very mixed performance capabilities. So the thought was, okay, let's imagine, you're a practitioner, you have like some large VIT that you've trained, for some sort of predictive task that you have, and you would like the benefits of an ensemble, but of course you don't have enough compute budget to train, two, three, four, five large VITs. Could you get some of the benefits of an ensemble by, say, combining this, like the predictions made from this large VIT with a model that required a lot less compute? So again, like a Resonant 18. If we just like look at these two models side by side, the VITB making one prediction with it is 17.6 gigaflops. With this Resonant 18, it's 1.8 gigaflops. So really, like, it's in some sense, it's like just a fraction of the compute that a VITB would have. If there was like some way to, use this additional information in this Resonant 18 to improve the prediction of the VITB, it's like you'd be getting performance improvements with relatively little additional compute. But um, the glaring problem here is that there's a wide discrepancy in the accuracies of these two models, right? So we have the VITB, like if we just think about its accuracy on ImageNet, it's like 86%. That's, very high, very good these days. With the Resonant 18, it's 72% accuracy. So if we just think about naively ensembling these two models together, right, that's just going to be net detrimental. This a little bit of additional compute that we would be using the Resonant 18 for would actually just harm our performance altogether. At least like intuitively, that that would be the case. Right. Would this, if we tried to think about a way to ensemble these two predictions together, would we just basically end up in a scenario where the incorrect predictions from the Resonant 18 are just polluting what would have otherwise been really good predictions from the VITB, and would have just been better off just using this large model in isolation? Well, if we go back to again this idea about this equivalence between um, single very large models and ensembles of still overparameterized, but like relatively smaller models, I can now think about maybe this VITB. I could think about it as an ensemble of M ResNet 18s, or some sort of equivalence there. And so now if I think about trying to ensemble these two models together, right, I could think about this as a way, like effectively as the VITB is an ensemble of M resonant 18s. And now if I add this additional resonant 18, I would be going to an ensemble of M plus one resonant 18s. And of course, it's not going to be a perfect equivalence, but like if I think about it like that, maybe it's actually not such a stupid idea after all to try to combine these two models with different predictive capabilities. And again, in such like a naive fashion, it's just like trying to average their predictions together. So in practice, what we do is a very simple procedure. We're just going to do a weighted average of the predictions made by these two models, and we're just going to learn, rather than trying to, figure out what is, what is the formula that gives me the like, equivalent number of ensemble members in the larger model. We basically just learn, the weighting parameters of how much, the how what the convex combination of these two models looks like. We're just going to learn that on a small validation set. It's like one parameter, so it's like we don't really need a huge validation set to, learn what the optimal mix of these two models are. And what really blew us away is that this kind of just naive ensembling, where it's just kind of a weighted mixture, was remarkably effective. So what I'm showing here is now a plot and this is now on each of these plots represents a different data set. What I'm showing here is, and also a bunch of different architectures. Um, so each of the architectures that's listed on these plots is that big model that we're starting off with. And now we're thinking about adding a single additional model that's going to be a lot smaller to ensemble with it. Um, the relative size of that small model is what's captured on the x-axis. So that's the flops balance. So if I have, say, a flops balance of 0.25, that means that the smaller model that I'm ensembling with the, say, VITB roughly is about 25% of the number of flops that I would need to compute a forward pass. And the diagonal, or sorry, the dotted red lines demonstrate what would be the accuracy of just the single large model in isolation. And kind of surprisingly, what we found was that this strategy, generally, it didn't matter how small we made that uh, the sort of additional model that we were adding to the ensemble. Basically, it never ended up, or in some, it only really seemed to hurt the prediction that we would make in these very extreme scenarios where the smaller model was maybe like 1% of the amount of compute of the larger model. In general, it seemed as if this ensembling strategy was either, net neutral or even potentially beneficial, despite the fact that these smaller models that we were ensembling with the larger models could be, uh, only like 75% as accurate as the larger model. And this really surprised us that, like the predictions that we're getting from these smaller models aren't polluting the large model predictions. In fact, they can be net beneficial. This performance improvement that we saw, though, and this is where I found things to be quite promising. This performance improvement only went up when we thought about, not just like looking at accuracy, but if we thought about and uncertainty, and in particular, using uncertainty on downstream decision-making tasks. So, kind of an easy one that we could test out was this task of selective classification. For those of you who might not be familiar, selective classification is basically, you can imagine it's like classification, except that I have a withhold option. So I could basically choose to, um, so like I'm going to make predictions on a bunch of data points, and I can basically choose these are the predictions that I feel confident in. These are the predictions that I'm going to withhold to, say, ask a human expert or ask an auditor to go over. And so typically you're using sort of like some sort of uncertainty signal that you get in the predictions as the signal to be, do I, go forward with this prediction or do I withhold it? And there's many metrics for what makes for good selective classification. We're looking at this SAC at 98 metric, which is basically saying what is the number of or what is the percentage of samples that I'm actually going through with that I'm not withholding from this model if I'm holding myself to an accuracy constraint of at least 98%. So I'm guaranteeing effectively that of all of these samples that do end up going through, they're going to be 98% accurate. How many then actually go through this model versus, the numbers that I withhold? So higher is better in this case. And what we found is basically on almost all these data sets, again, really regardless of the amount of computation you're getting from the smaller model, this generally led to much better selective classification performance. So we could see actually some pretty sizable improvements. Again, when we're adding on, and this is again just a very naive ensemble, just like a simple weighted average of these two predictions. If we added a model that was, again, a fraction of the compute, so like you could think about that, a fraction of the accuracy of this larger model, we could see very significant gains in selective classification or downstream decision making performance. And again, I think if you're thinking about this with sort of like classic ensemble brain, feels super harebrained and doesn't really make sense because why is the small model not polluting the predictions of the large model? And I think the way that we can analyze it now is again thinking about that large model is effectively acting like an ensemble of many smaller models. And so we're just effectively building a bigger ensemble due to this connection that we have. Um, so the takeaways then from this part of the talk is that in this sort of new overparameterized world, especially when we're thinking about uncertainty quantification, we're in the upside down. All of our intuitions are basically backwards. Like conventional techniques like bagging or subsampling or, thinking about, sort of like simple wins for increasing the predicted diversity can end up harming the accuracy of ensembles when we're thinking about overparameterized models. But some of these like unconventional techniques where, we might get laughed out of the door if we even propose them might actually work and could be beneficial, both for accuracy, but also for downstream decision making. And so I think moving forward, effective ensembling really requires foregoing kind of these classic intuitions that we have. And with that, I would like to thank a whole host of collaborators that made this work possible, especially Tyga, Kelly, Nicholas, and Tim, who were the first authors on all these works and really did a bulk of the work here. And with that, I'm happy to take any questions.
Questions? Yeah, question.
Hi Jeff. Yeah, thank you very much for your talk. I really like the visuals and the flow of your talk. One question I have is for the asymmetric dual, and we
Yeah.
know that the improved selective classification performance can come from just the improved accuracy itself, right? Do you think here the improved classification performance, it comes from just pure the accuracy improvement, or it comes from a better uncertainty quantification here on this case?
Yeah, that's a really good question. I would say you're absolutely right that the better, like, there is going to be some component. We're not like, completely decoupled here, right? Because if I go back one slide over here, we do end up having, like these asymmetric duos are more accurate and more accuracy would lead to better selective classification performance. I would say it's not necessarily on this plot, but effectively what we found is that this additional increase in selective classification performance seems to exceed the additional benefit that we get just from increased accuracy. And perhaps more surprisingly, what we found was that if we say compared this asymmetric duo to like sort of a classic deep ensemble, we found that the asymmetric duo um, generally led to better selective classification performance than the ensemble, even like the sort of the classic ensemble, even though the classic ensemble had roughly the same, if not more accuracy than the asymmetric duo. So it's not totally captured by these plots. And of course it's like there is definitely some confounding here. So that's a very good question. But I do think that there is it's not strictly just the better performance. I do think that there is some sort of uncertainty that's being captured here.
Yeah, thank thank you very much. I have a follow-up question. Well, I have a more open-ended questions. So the
Yeah.
results on your slides are more on the classification model.
Yeah.
Do you have some comments on the generative model, or do you see if there's any challenges or difficulty of generalizing your results to the generative models?
That's a really good question. I've been thinking about this a lot. Like, how do these results extend into the generative setting? And there, I actually don't know if I have anything too intelligent to say there. I think that there's still sort of a lot of thinking that I'm doing here. I know that I have, some collaborators who are interested in thinking about could some of these duo ideas, potentially apply in a generative or an agentic setting, where we're thinking about potentially like having, smaller models be, verifiers or helping out in some particular way there. But at this point, it's all super speculative. And, if you have any good ideas, I would like love to hear them or talk about them some more.
Okay,
Thank you.
there's another one. Yeah.
Thanks for the talk. Actually, I have a question about the comparing between a small model and large model. Because
Yeah.
when trying to create a large model from small model, we can either increase the width and we can either increase the depth.
Yes.
I wonder whether for these two options, you see any difference compared to the in terms of ensemble. Because for the MLP, people are more likely to increase the depth instead of the
Yeah.
width for the model capacity, right?
Yes. Yeah. Yeah. That's a very good question. So, right. Are we there is, very much a difference. Like I think you're right. People are much more likely to increase depth, and depth generally, tends to be at least more parameter efficient towards creating better predictions. So that definitely is something to uh look out for. I think when we were doing a lot of our comparisons here, so at least in this duo's work, we were typically we were kind of conditioning on the number of, floating point operations, as that was sort of our way of measuring model complexity. And because we were using a variety of different architectures, it was like, kind of hard to compare width and depth because, what does like width and depth and like a vision transformer compare with, width and depth and like a residual neural network? A little unclear there. In some of the earlier comparisons, that I made in sort of the first part of the talk, there we were typically just sort of we would, especially because we were trying to think about ensembles of matched accuracy models, we would just sort of like typically think about like, okay, maybe here's our ensemble of ResNet 18s, that gets a let's say 78% accuracy on ImageNet. So let's now find a single model that also gets 78% accuracy to try to make those comparisons there. So that was a little bit also trying to sidestep this width and depth issue as well.
Thank you. Uh, I had a question on the previous slide.
Yeah.
Or sorry, where you combined like the VIT and the ResNet?
Yeah.
Yeah. So my intuition is that like the VIT and the ResNet are like very different like models, right? So it's basically just due
Totally.
to the increase in predictive diversity, right?
So that's a really good question. And so I guess I'm gonna say two things about that. So the first is they are very different models, but when it comes to actually the predictions that are being made, they're not actually as diverse as you would expect. There was this really good paper from in 2022 iClear. I'm blanking on the author names, which is I'm sorry to say about that, but it was called "No One Representation to Rule Them All," and what they found was basically like, so what they were considering was like, let's consider again these like ensembles of two models. We'll think about, okay, here's two ResNet 50s. Um, you know, okay, like each of these on their own get like 78% accuracy. When we ensemble two of them together, we get like 79% accuracy. Now, what would happen if I ensembled a ResNet 50 with a VIT, and that would now maybe bump me up to like 80%. But then that pales in comparison to say, well, what if I trained these two ResNet 50s on two different training data sets? Then that like bumps you up into the like high 80s range. So there's like the differences in these, like there is some predictive diversity between a VIT and a ResNet and ResNets, but it's like not quite as much as you would think. And that's kind of that I think is also sort of captured in this graph over here, where we see like as models become more powerful, even with diverse architectures, they start to become less diverse. But I think though the I think also on top of that, right, like there is this huge accuracy discrepancy between the two of them, which of course is going to be predictive diversity. Because if one model is making worse predictions, like a lot worse predictions than the other, like they're clearly not making the same predictions. But so like there is a little bit of predictive diversity in there. I totally agree, but it's less than you would think.
Thank you.
I have two questions. So first one is actually if an ensemble is basically equivalent to the one single network or larger model, in what situation does the ensemble still give more uncertainty? I mean, give more trustworthy uncertainty, especially on the distribution shift and OD. And what evaluation could you trust to prove that? The second question.
Yeah, so that's a really good question. Right, so like you are getting from this on an ensemble, you are getting this additional signal, which is the variance amongst the ensemble members, and there's not necessarily a way to recreate that from a single model per se. I think that I would say you're getting sort of like marginally better predictions. Um, because I think that like you could sort of think about like this additional signal that you have in the variance is some additional data, but it's definitely not like this totally orthogonal signal that's providing something fundamentally different than what you could get from, a single large model. So you could kind of think about like, there's like a tight correlation between the variance and sort of signal that you're getting from any single model in isolation. So like, of course, they're noisy. So like, if you are using that variance you're getting from a model, I would say you are like you're averaging out a little bit more noise that you would have had in the procedure. So it's like it's a slight, potentially like a slight improvement for things like out of distribution detection than what you would get from a single model in isolation. But I really think that I mean, I think especially with something like out of distribution detection, I think there's a whole host of methods that don't rely on ensembles that people have come up with when thinking about out of distribution detection. And so I think that this I'm still sort of like trying to investigate like, okay, well, if ensemble variance isn't the answer, then what is? And I think that I'm not necessarily sure I have a great answer to that question. But I would say that ensembles are never bad to use. Like in fact, like ensembles can be really great. Like if I can basically get the same performance from an ensemble versus a single large model, an ensemble is way easier to train, right? Like I can parallelize that very effectively over many GPUs. I will get this variance, which shouldn't hurt me, necessarily, but it's not necessarily going to be this like fundamentally different class of models that's giving me, performance guarantees and like uncertainty that I can really, trust on its own.
Okay, thank you. And a very quick question about
Yeah,
selective prediction that
yeah.
even though the accuracy is similar, but will they make a same decision? Like if we set a confidence cutoff, like all the cost sensitive threshold, will they agree or disagree on which examples are safer to answer, make a same decision?
That's a really good question, and I'm feeling a little embarrassed now that we actually didn't look into that. Yeah, that's definitely something we should analyze. Because I don't have the answer for you. But that's a really cool experiment that we should definitely run.
Yes. Uh, Thank you for the talk. In your first first part of the talk, you
Mhm.
mentioned and showed how excuse me, ensemble can be in over parameterized regimes, especially so neural network ensemble can behave as a single large model, and the predictive variance is not actually the uncertainty we would assume, but it is like reflecting somehow capacity, which you mentioned, right?
Mhm.
So
Yeah.
to capture the real epistemic uncertainty, what would you suggest? You suggested this asymmetric duo ensembling for like diverse ensembling, but do you think it captures the epistemic uncertainty?
I really love the asymmetric duo work in part because I was just like so surprised that it worked. And like it's also like it's quite a practical recipe. Uh but I think that right, I don't really think that any of these techniques are necessarily capturing epistemic uncertainty. I think the best kind of, or I would say, right, like epistemic uncertainty is basically, right, we're going to be thinking about what is the uncertainty due to my model. And I think in some sense, right, like that's kind of like thinking about how would I expect my predictions to change if I added more data or if I had used a different data set. And so I think that the best approaches I've seen for epistemic uncertainty, or at least like the ones that I feel that I'm potentially most excited about, is thinking about ensembles of models that are trained on different data. And now I think if we're thinking kind of from a, say, like more, uh, you know, classical perspective of machine learning, like that's not necessarily the most or that doesn't necessarily sound super advantageous, right? Because it's like I'm thinking about, okay, here's, like some training data that I've collected, and now I'm thinking about like, okay, I can train models and I could, think about training a bunch of models on some subset of this data or training the models on all of the data. Well, really the like training the models on all of my available data, like that's the obvious recipe that I should have, right? Like if I have, here's a neural network, it's going to be way worse if I'm only training it on a subset of data. I think now, though, in this sort of like new foundation model paradigm that we have, I think this creates an exciting opportunity for thinking about, well, what if I have, a model, like if I'm thinking about here's some sort of foundation model that was trained on, this type of data, and here's it, or not even, I guess maybe to make it a little bit more concrete, like let's imagine that, okay, here's a foundation model for some, say, like remote sensing task that's trained on data collected in the United States. And now here's a different foundation model that is trained on data that was collected in Canada. Like this is a common paradigm, like especially now thinking about, especially in kind of like spatial temporal applications where we might have like foundation models trained on like different geographic regions. And now, if I think about fine tuning some of these foundation models and creating an ensemble this way, um, now I think that we're starting to like really capture epistemic uncertainty. And I think there's some really cool work that has looked into this paradigm where we have large foundation models that are trained on different sets of data. How do we think about combining them? Again, just using kind of really simple ensembling techniques, but I think that's going to be a much more meaningful way to capture epistemic uncertainty. Because I think if we're just using the same data for all of our models, at the end of the day, most of what we're going to capture is just the inductive bias of SGD. And there's not going to be a lot of differences amongst the predictions. It's only really when we start getting different training data that we start capturing differences.
Okay. Yeah, thanks, Geoff. Thanks for the great talk and answering the questions. I guess if there are no more questions, then let's
One last thing. Okay.
Do you have any intuition as to why for ConfNext the performance increase is like not as much as the other ones?
Yeah, okay,
Like,
that's a good
ImageNet
question.
is also like a CNN.
Yeah, well, yeah. This plot's a little bit conflated because it's both ConvNext, but it's also a different data set. This is the ImageNet V2 data set. So this is the model that was trained on ImageNet, or fine-tuned on ImageNet in certain cases, but then where we're testing on this ImageNet V2 data set, which is basically like a recollection of the ImageNet test set, which is known to have some like distribution shift. I think it's mostly like a long tail distribution shift. So my assumption is that because it's a little bit more, this is a case where the data is a little bit more out of distribution, I would say, as opposed to the architecture. But then moving two plots over, we have this iWildCam OOD data set, which is again is going to be sort of the similar like out of distribution data set, and there things start to seem to improve. So I don't know. I don't really have a a good answer. I think I think it's probably more peculiarities in the ImageNet V2 data set.
Thank you.
great. Thanks, Geoff. Thank you, Geoff, for your time today.
Yeah, thank you.